Welcome back to Unit 11 on vectors. Today's lesson day 3. We're going to derive and use a new tool called the Law of Cosines, used for finding missing pieces of triangles, both sides and angles, when the law of sines can't get the job done. As a warm-up, let's use this triangle here, angle 37, sides 4 and 3. We'll find x to begin with, then we'll find the remaining sides and angles, then we'll find the area. I'll take a second to pause. You can check your work. As I'm sure you saw, it was an SSA. 37, 4, 3 gave us two triangles possible. My first work I did was in red. I had the side angle pair of 37 and 3. I went through sine of 37 over 3 equals sine of x over 4. I got one possible angle x to be 53 degrees. The supplement, also 127. Were there degrees left to make both triangles? 37 and 53 left c of 90. 37 and 127 left c of 16. So indeed, there were two triangles possible. I then used the law of sines. Actually, for the first triangle, c being a 90, it's a Pythagorean triple. 3, 4, c would be 5. In the other triangle, the green work right here, sine of 37 over 3 equals sine of 16 over c. I found side c to be 1.4. Then to add a nice little addition to our review, area formula, 1/2 AB sine of c. We talked about that as being a corner. There's our corner right there, side 4, side 3. My first triangle, triangle 1, area 1, 1/2 AB sine of c. 1/2 4 times 3 times sine of 90 is 6. Area 2, 1/2 4 times 3 times sine of 16 is 1.7. Here's another example if you want to try on your own. It's in my notes, posted on Schoology. I also have a third, if you want to try that as well. Next, we're going to derive a new tool called the Law of Cosines. And here's what we're going to do. We're going to take this triangle. We have side B at the bottom, angle B at the top, angle A to the bottom left, angle C to the bottom right, and opposite sides A and C. This is mathematics, folks. We're going to derive this. Couple ground rules. We're going to use the left triangle in terms of the right triangle. And 2, we're going to express all in terms of A, B, and C. No imaginary x, part of it, no altitude y. All right, let's create a couple nice, easy formulas to begin. I'm going to create something on this left side in green. I see a Pythagorean theorem. X squared plus y squared equals c squared. Now I'm going to move to the right side. I'm going to do this in red. Give me two equations using angle C. Sine of C equals y over A. Cosine of C equals B minus X all over A. If I take equation 1 and solve it for y equals a sine of c. If I solve it for x equals b minus a cosine of c. Why did I do that work in red? So I'm going to go over to the green and replace what x is and what y is. Again, our goal, everything in terms of a, b, and c. X can now be replaced. B minus a cosine c squared plus y can now be replaced. A sine of c squared equals c squared. Take a break. Again, not something I would expect you to be able to do, but you should be able to follow this along. When we get this great tool at the end, you know it wasn't just some magic hand waving. It was something we figured out, derived, and can use it effectively. If we have to take this binomial and square it, we got a FOIL. Let's do that real quick. B squared minus 2ab cosine of c's plus a squared cosine squared c. Take a look at that. That should make sense to you from that binomial. Plus a sine of c squared is really a squared sine squared c equals small c squared. Next, again, mathematicians see things like this. They're trying to come up with valuable tools. I'm going to regroup. I see something right there. B squared minus 2ab cosine of c plus a squared cosine squared c plus a squared sine squared c equals c squared. What did we learn last unit about sine squared plus cosine squared? Equals 1. If I pulled that a out, what I would have is b squared minus 2ab cosine of c plus a squared times 1, leaving me with this great tool. Clean up, put in our law of cosines box. C squared, any side squared equals one side squared plus another side squared minus 2 times the product of those two sides times the cosine of that included angle. Very, very powerful. Take a look at that. That's where it came from. Again, not expecting to come up with the derivation yourself, but to see where it came from. Let's use it. I have a triangle here. If I can, I'm going to use the law of sines. It's easy. It's proportional. I don't have a side angle pair, and I can't obtain one. So, can't do it. That tells me I've now got to use the law of cosines. That's the side I want to find. That's the side that goes by itself. X squared equals one side squared plus the other side squared minus 2 times one side times that other times the cosine, law of cosines, remember, of that included angle. Plug those numbers in. X squared equals 25 plus 49 minus 70, cosine of 39. X squared equals 19.599 square rooted. That x is a 4.4. If we wanted to, we would now have a side angle pair, 39 and 4.4. We could go and use the law of sines to find those other two angles, hence solving the triangle completely. All right, so where does that put us? Let's take some good old geometry terms and let's decide what law we can use to solve. If at all possible, I'd say go with law of sines if we can. If not, we have to go cosines. Let's draw it first. Any side angle pair, if I've got a 63 here, I've got a 10 there, and an x, I know I can use law of sines. I've got my pair. Next situation, angle side angle. Let's draw it. From geometry, I know what that means. 20, 10, 48. Can I get an angle side pair? I sure can, because that angle adds up to 180, so I can use the law of sines in any ASA situation. Case 3, AAS, another triangle congruence method. If I have AAS, 42, 6, 61. Again, any two angles generates the third, so I can get a law of sines angle side pair. SSA, Ambiguous case, that's what the star means. S4, S7, angle 51. Yes, I can use the law of sines, but I got to remember two triangles, question mark. Last two, SSS. We have only three sides, 3, 5, 6. No way of finding any side, no way of getting a pair. That's where the law of cosines comes in. And our last case, triangle congruence, SAS, guarantees two triangles are the same. If I have a side, 6, an angle, 81, and a side, 7, no way to get a side angle pair. I've got to use law of cosines. Keep that chart. That's going to tell us which tool we're going to have to use to solve for the missing triangle, along with an illustration to represent it. Let's move on, do an example. Here we go, side, side, side. Well, if we're going to pick our law, we know we got to use cosines. The more we write it, the more we memorize it. C squared equals A squared plus B squared minus 2AB cosine C. Now, this might trigger something. Wait a minute. Isn't that just the Pythagorean theorem? How can we subtract something and still have it equal? Well, remember, if C squared is the hypotenuse, that makes angle C 90. If it's 90, what's the cosine of 90? We all know to be 0. It wipes that whole term out. So therefore, the Pythagorean theorem is one specific instance of the law of cosines where that angle's 90. Law of cosines, however, works for all triangles. Pythagorean theorem does not. So let's go back to our example. I'm going to find this angle x, which means in the law of cosines, that 7 has to get by itself. 3 squared plus 5 squared minus 2 times 3 times 5 times cosine of I don't know. If we take a look at that, we can do some number crunching. 7 squared, 49. 3 squared is 9 plus 25, 34. 5 times 3 is 15 times 2 is 30. Cosine of x. Now be careful. What do we do next? We do not subtract 34 minus 30 because the 30 is connected to the cosine of x. Instead, we subtract off the 34. 15 equals negative 30 cosine of x. Divide by negative 30. Negative 15 divided by negative 30 is negative 1/2. Cosine of x. X equals cosine inverse, negative 1/2. Talk about something that brings back the past. Last unit we said cosine inverse of a negative ratio is a second quadrant angle. The calculator generates 120 degrees. We now have side angle pairs. We can finish this problem up. Let's do it since it says solve. We can now go sine of 120 over 7 equals sine of y over 5. Y equals 38 degrees. And then we can say the third angle, z equals 180 minus 120 plus 38. Z equals 22. And we've solved the triangle. If we wanted to, we could pick a corner, find that area. A equals 1/2, 5, 7, cosine of 22 equals 16.3 square units. All right, so there's an example of side, side, side using that law of cosines.